We're going to go over Cartesian equations in two space. And specifically, we're going to go over the Cartesian form of an equation and how it relates to normals. Okay, so we're going to be working in two space. Our Cartesian form is usually written as the coefficient of ax plus by plus c is equal to 0, where our normal, the coordinates of our directional vector for our normal, are actually the values of a and b. Okay, so we're going to talk about that using other forms, and we'll briefly also get into when we have two normals, how we can discover if lines or vectors are parallel by comparing scalar multiples of the normals, and the dot product of those two normals. If the vectors are perpendicular, the dot products of the normals should be equal to 0, or in other words, they should also be perpendicular. We'll do this one in another lesson. Okay? So, they've given us our vector form of this equation. So it's in vector form, and we want to put this in a Cartesian form, which means we need to find the normal to this vector, and specifically the directional vector. We know that the normal is just a negative reciprocal of the slope, so by looking at this, we can find the slope of this equation quite quickly. The slope, if we were to talk about it in y-intercept form, would be negative 2 over 5.
Nathan, please come.
So if the slope is negative 2 over 5, that means the slope of our normal should be positive 5 over 2, which means as a directional vector, okay, let's give it the scalar or the parameter of s, our coordinates would be 2 and 5. So when we look at it in this way, essentially we're just switching the positions of the numbers, and if one of them is negative, we're making both positive, and vice versa. Okay. Now that's of the normal, and the normal, we don't know what point it technically wants us to go through. So if we want it to be normal to the original vector, we'll just use this coordinate as the other part of the normal, because we know that this normal will go through that point and is perpendicular to our original vector. Now this will help us with our Cartesian form. Remember, the Cartesian form is written as ax plus by plus c is equal to 0. We know that our normal related to the Cartesian form is the normal of the directional vector of the normal, the coordinates of it, so this being our a and this being our b, are directly related to the Cartesian form. So we can replace a and b once we know the directional vector of the normal. So our a value in this question is 2, x plus, and our b value is 5, y plus c. Now the only unknown variable that we still need to solve for is our c in this question. And since we already have a coordinate along this point, sorry, I meant to point to this vector, not this one. Since we already have a coordinate of this vector, the Cartesian form of this vector, we can plug in the x and y value for the x and y here to isolate for our unknown c. So the coordinate in our vector of negative 3 and 1, being an x and y value, can we plug directly in? So we have 2 times our x value, and I guess we'll do this in blue, of negative 3 plus 5 times the y value of 1 plus c is equal to 0, which will give us negative 6 plus 5 plus c equals 0, which will give us 1. I believe. Well, it'll give us negative 1, and we bring it over, c is equal to 1. Is that right? Yeah? Okay, good. So the Cartesian form of our vector is 2x plus 5y plus 1 is equal to 0. Okay? With that being said, if we wanted to find a line, or sorry, I keep saying line, but a vector, if we want to find a vector parallel to this vector here, it's actually very simple in Cartesian form. They've given us this rule here that the normal, if we're looking for two parallel vectors, are just scalar multiples of the original normal. So we just have to find a scalar multiple of our Cartesian form to find a line that would be parallel to our other one. So we know that the normals need to be parallel. And in order for our normals to be parallel, that means we have 2x plus 5y. And I'm going to leave this as the value of c, because if I rewrite it as the value of 1, this is obviously the same equation. Okay, so let's say we have a scalar multiple of the original one. I want another one. Sorry, I gave us the exact same directional vector. Let's do another one. Let's say it's a scalar multiple of 2. So our idea being 4x plus 10y, and I'm still going to write this as just the value of c, not multiplied by 2. And the reason I'm doing that is because if I just take these values and multiply them all by 2, so I come down, this becomes 4, this becomes 10, and this in this case would be 2. These are actually the exact same vector. Okay? It's one on top of the other. If the c is different, but our a and b are scalar multiples of the one before, that means it is parallel going through a different point. Okay? So it's not the identical vector. So we can give our c a different value, which means this would be parallel to the one above, not coincidental. Coincidental means there's one on top of the other. So if I gave this a value of 2, then this would be coincidental to the one on top. If I give it any other value, 5, 8, a billion, it's parallel but not coincidental. So they're not two vectors on top of each other. And if we want to find something that is perpendicular to this, we know that the normal, actually, sorry, let's go back to the original one just to keep it simple for ourselves. This being our directional vector of the normal, 2 and 5. If we want to find perpendicular to that, okay, and this is perpendicular to the normal, we essentially go to the directional vector of our original one. So we flip these coordinates around. It could be negative 5 and 2. And the Cartesian form of that would be negative 5x plus 2y. And again, we just find a value of c. And this would be a perpendicular vector. If we found the dot product between the two, it would be 0.